Hi, good morning everyone. I hope you enjoyed week 3's lectures. Particularly we started programming in Verilog and we will see Verilog programming every week from now on, and this is probably new to many of you. So what I suggest is you start writing small Verilog modules time and again, so that you get used to the fact that you are not just designing circuits, you are also writing a program which models the circuit that you want, which is amenable to evaluation. So if you did the circuit in a piece of paper, I would have no way to check it, but if you write Verilog code which describes the circuit, I have ways to check it even from here. So we are now in week 4, and in this week we are going to look at basic sequential elements. So let me give you a small motivation for this problem. So in hotels they have what is called housekeeping. So let us say a guest who is living in a room wants to leave the room, but wants to get it clean when the guest is away. So what the guest wants to say is, I am going out now, please clean up the room before I come back. And one way in which this can be done is the guest can press a button, let us call it set, saying that the room needs cleaning, and let us say that this turns on a light outside and indicating that the room needs cleaning. So the housekeeping staff, when they move around, they can see that the light is turned on. So if the light is turned on, it is an indication to them that the room actually needs cleaning, and the guest has left a message in some sense for the room to be cleaned. So some housekeeping staff can go clean up the room and then press another button which resets the light. So one thing that you have to do here is, the staff member should go and turn off the light later, otherwise some other housekeeping staff, when they come around, they may still see the light turned on and they may go and try and clean the room once more, and so on. So what we want is, we want a mechanism by which there is some kind of a signal left by the guest when the guest leaves, and when the guest comes back, if he sees that the light is off, he will know that the room was actually cleaned. If the light was still on, he will probably know that the room was not cleaned so far. Right? So this is a setup that we want to take care of. So this is a common thing in hotels. So I may go to a city for some conference, and I see that so I leave in the morning, but I want the room to be clean, so that when I come back in the evening from the conference, I have a clean room. Right? So this kind of setup is very common in hotel housekeeping, and there is a small motivational problem. So as a circuit, what we want is, in some sense, I as a guest must be able to set a housekeeping request, and it should remain 1, because I press 1. So let us say I set a request and then I leave. You do not expect me to sit there and keep continuously making requests, right? So once it is set, it should remain at that till the housekeeping staff comes, cleans, and then resets it. So this requires some kind of a memory element. It is not an instantaneous thing. So remember, when we did combinational circuits, I said the moment something changes, the input, if the input changes, the output changes, and as soon as the input is removed, the output may or may not change. In this case, right, what we want is, even if the input is removed, so I press a button saying I want I need a request for this, it sends a signal called set to a circuit block, and I may leave it. That signal is not going to be on anymore. I may not have the signal anytime, but this should be kept in the memory, which means the light should keep turned on till the housekeepers come and reset it. Again the same thing, once the housekeepers reset it, it should remain, because they are not going to keep pressing the reset till I return back to the hotel room, right. So they press a reset button and they leave, and the memory system should keep it, the system should keep this in their memory, and when I return back, if I see that the light is off, so I would know that the reset button was pressed, which in fact means the housekeeping staff came and cleaned the room. So this requires a memory element. We need to remember what was the state even if the input was removed. So there is a crucial difference between what is called a combinational circuit block versus a sequential circuit block. So in a sequential circuit, steady state outputs are a function of the current inputs and the past inputs also. So the circuit does have some memory. So when I say current and past, it also means current and future, right. So if I store something now, it is available for the future, it will be remembered for the future also until some other condition happens. So what this means is, in terms of the circuit, there is actually some feedback path. In the circuits that we have seen so far, there is you start with the inputs, and then these feed some gates, and these feed some other gates in turn, and so on till you have the output. At no point we had a wire coming back from output of a gate to somewhere in the input of the circuit. That never happened so far, but for memory you need this feedback path, and the state of the circuit is actually registered as the state of the memory. Let us see a very simple memory element. So let us take two inverters and connect them back to back, right. For a moment, in this case, right, there is no external input. For a moment, let us assume that this B is actually 1. If B is 1, you would expect that this inverter will drive a 0, and this being a 0 will again keep B at 1. So B will remain in the steady state of being 1. However, if B is 0, then 0 complement will be 1, that goes as A, and then 1 complement would come back as B. So B would still remain at a steady state, but at this point the steady state would be 0. So what the circuit does is, if B started at 1, it will remain at 1, if it starts at 0, it will remain at 0, and it will stay there forever, so provided there are no disturbances and so on. So the key thing is, this circuit does not have any input at all. So in that sense, it is a very uninteresting circuit. You cannot really do anything with this, even though it remembers the value. No matter what the value is remembered. However, it does not have any external input, right. So we need a memory element which can remember the value in some sense. So go back to the problem I gave, we need to remember the set as well as the reset given to the circuit. So we need something like that, and it has to remember. So these are the three things. So to do this, we have different kinds of basic logic elements. Latches and flip-flops are the basic building blocks of sequential circuits. The first thing is that these devices, both the latches and flip-flops, are what are called bistable devices. So a bistable device is one in which, if you are at logical level 0, it will remain at 0 and it is a stable state, and if you are at logical level 1, it will stay at 1 and that is also a stable state, unless there is a condition which moves it to the other state. So this is unlike a circuit like Schmidt trigger, for instance, which is a monostable multivibrator. So it's in one state, ground, so let us say it's in 0, and you trigger a Schmidt trigger, it may go to 1 momentarily and then come back to 0. So it's a monostable multivibrator because there is only one stable state, but it can be in two different states. So the one state is transient in Schmidt trigger, whereas the 0 state is the stable state. Whereas in a flip flop, both the states are stable, or in a latch, a flip flop or a latch, in both these different logic elements, both the 0 state and 1 state are stable. So many times when you talk to people, right, they may actually go back and forth between latches and flip flops, and they may not make a specific distinction between those. So however, in this course we will be very careful about what a latch is versus what a flip flop is. In fact, there are crucial differences. An experienced person may actually lapse and say one for the other, but usually from the context that they are talking about, it is usually clear whether they are talking about a latch or a flip flop. But for this course, we will be very careful about what a latch is versus what a flip flop is, and in the real world also it is actually important. So let us do this memory element slightly differently. Earlier I had two inverters, right, which were connected back to back. Instead, I am going to put two NOR gates which are connected back to back. So there is a NOR gate whose output feeds into another NOR gate's input, whose output in turn feeds into the first one's input. Right. So there is a feedback path. This would not happen in a combinational circuit. In a sequential circuit, we will have feedback paths, and we have two different signals, namely reset and set. So this is a memory element with NOR gates. We will see why this acts as memory and what kind of circuit it is and so on in more detail now, but because there is feedback, there is some notion of memory. So we will get to that in a little while. So the first kind of logic element I am going to talk to you about is something called SR latch. It is the most basic sequential circuit, so it is very fundamental, and we will use this SR latch to build other latches and so on. So we will use this as a basic block to explain other things. So what you see as a circuit here in the bottom is actually the same circuit that I showed earlier, except that it is drawn in a different form. So you take a look at this circuit. So there is some signal called a set, there is some signal called a reset, and there is an output called Q. So there are two inputs and one output in this circuit. The same circuit is redrawn here. So there is a signal called S, there is a signal called R, and there is an output called Q. On top of that, there is another output called Q bar, which is actually this line. Right? If I tapped out this one and gave it as output, we will call that Q bar. Right? So what it actually has is two signals, namely R and S, and let us say R is going to stand for reset and S is going to stand for set. We will get to that in a little while, and we will have two outputs, Q and Q bar, where Q is the complement of Q bar and the other way around. So this is the basic definition of a SR latch, but I first want you to be convinced that this is going to behave, this is going to remember the values. We will have to be convinced about that, and later we will have to be convinced about whether R actually resets it, S actually sets it, and so on. We will see that in detail from the next slide onwards. So the same circuit is given above. So this sub figure A is the actual circuit, and the way it behaves is actually given as a table here. Okay. So let us assume that there are two outputs QA and QB for a moment. Instead of Q and Q bar, I am going to assume that these are two different signals, QA and QB, and as of now we do not know the relationship between QA and QB. Let us start with that, and let us assume that there are two inputs R and S. So what we see here on the right side is a table which describes what is going to happen because of the circuit. So let us start with the case where both S and R are 0. So if both S and R are 0, right, so what would happen? Because R is 0, if R is 0, QB or 0 would be QB complement. So let us assume in fact that, so R is 0, S is 0, and let us assume that QA is 0 and QB is 1 for a while, right. Let us assume that if QA is 0, then S being 0 will take QA or S, which is 0, complement of that QB will become 1, and because R is 0, you have 1 or 0, that is a 1, and the complement of that will go to 0. So QA will remain at 0 and QB will remain at 1. Let us assume the same thing where QA was 1 instead. If QA was 1, then 1 or 1 is a 1, but there is a complement here that will drive QB to 0, and 0 or 0 is a 0, the NOR of that is actually a 1, so QA will be at 1. So you can see that if QA is 0, QB will be 1, and if QA is 1, QB will be 0, and when you apply 0 0 as inputs, they actually remain the same. So if you start with a 0 here, this will be a 1, but under the conditions given for R and S, QA will remain at 0 itself, it will not change, right. So this is one case. Let us go and see what happens when you have the other cases. So what you see here in the bottom is what is called a timing diagram. We saw something like this in the Verilog code last time. So we had signals which were in the y axis, and in the x axis we had time. So let us start with each of these timelines. There is timeline T1, T2, so on up to T10, and I am going to show you what is happening in the circuit, and we will also convince ourselves that this table is correct. So let us for a while assume that R is 1 and S is 0, and let us also assume for a while that R means reset. So, reset will drive QA to 0, let us assume that for a while, and we will also assume that S drives QA to 1. So, R being 1 is supposed to drive QA to 0 and S being 1 is supposed to drive QA to 1, and I also claim that QA and QB are complements of each other. So, let us assume that for a while. So, let us see this waveform without making any of these assumptions. Let us say that R is 1 and S is 0 for a while now, and QA is 0 and QB is 1, because if R is 1 then QA is 0, it is quite apparent, right. If R is 1, right, 1 nor 1 is 0, QA is 0. So, 0 or 0 is 0, but a NOR will give you 1, so QB will be 1. So, till T1 I think it is straightforward, these signals are all consistent with each other, you do not have to assume anything, just making R equal to 1 and S equal to 0 will imply what QA and QB are. Let us assume now at T1 R actually goes down to 0. So, this is a case where both of them are 0. So, both the inputs R and S are 0. So, I said that if both R and S are 0, QA if it is 0 it will remain at 0, and QB if it is 0 it will remain at 0. So, in this case QA is at 0, it remains at 0, and QB was at 1, it remains at 1. So, this is up till time T2. Now, let us assume that at T2 this green one is S, let us assume that S goes to 1. So, I said that the semantic attached to S is that it is supposed to be setting the value of QA to 1. So, let us see what happens. When S goes to 1, you can see that the effect of S going to 1 is not direct on QA. In fact, it goes and changes QB to 0, that is the direction of the arrow here. So, when you see a timing diagram and if you see an arrow coming from one signal into another signal, you can see the arrow here. So, it starts from here, but the direction of the arrow is from the green line to the purple line. So, the change in S is affecting a change in the purple line, which is QB. So, change of S from 0 to 1 will change QB from 1 to 0, right. So, it is shown as though it is instantaneous here, as in at time T2 itself magically this changing from 0 to 1 immediately changes, or simultaneously it looks like it is changing QB from 1 to 0. Usually it is not instantaneous, it requires a little bit of a delay, let us not worry about that right now. So, let us assume that it is instantaneous for now, it is actually changing QB to 1 and QB to 0. So, S changing to 1 changes QB to 0, and when QB changes to 0, you see what happens when QB is changing to 0. So, QB was earlier at 1, it is now changing to 0, and you see the condition for R at T2 is at 0. So, you have 0 nor 0, which is 1. So, QA becomes 1. So, you can see the direction of arrow here. So, S becoming 1 changes QB to 1, QB to 0, and QB changing to 0 changes QA to 1. Now, at this point let us say S went back to 0 at T3. So, if you look at time between T3 and T4, both S and R are at 0. So, QA will continue to remain at 1 and QB will continue to remain at 0. So, we have reached time step T4 so far. Now, let us look at the next change. At this point let us assume that R goes to 1 and S remains at 0. So, if R goes to 1, what is the effect of that? When R goes to 1, it will have an effect on QA, because QA is R nor QB, right. So, if R goes to 1, it does not matter what QB is, QA will go to 0 because of NOR gate there. So, you can see the cause and effect here. The cause is the tail of the line and the effect is the head of the arrow. So, the tail of the arrow is here and the head of the arrow is here. So, we can see that T4 is changing the red line to go from 1 to 0. So, QA is changing from 1 to 0. This is going to change the purple line or QB from 0 to 1. So, it is clear from this one that when R is 1 and when S is 0, QA is reset. So the word reset is used to indicate control changing the value to 0. It could be 1, if it is 1 earlier, it is actually changing to 0. If it is 0 earlier also, right, it will remain at 0. So reset means no matter what the input condition was, it will go to 0. So now we are at time t4, let us say the time passes, and let us say at this point t5, at t5 let us say S comes on, right. At this point both R and S are 1. So when both R and S are 1, it looks like, so I said the semantic for R is reset and the semantic for S is set. We want QA to be reset when R is 1 and QA to be set when S is 1, but now both S and R are 1. Let us see what happens. Both S and R are 1. So when both S and R are 1, what happens is, so this S changing to 1 will change QB to 0, QB is 0, R is 1, so 1 nor 0 is 0, QA also remains at 0. Right. So between T5 and T6, QA is 0 and QB is also 0. So it looks like both being 1 is driving QA and QB to both zeros, right. You can see, so you can see that here also, it is remarked here, with both are 1 is remaining at 0. Now let us say at T6, S again changes back to 0. If S changes to 0, then that changes QB to 1, because the conditions are that QA is already 0, S is changing from 1 to 0, so QB will change to 1, and QB being 1, and you can see that R is actually 1, so both are 1, QA will remain at 0, so there is no change in QA, there is no arrow like earlier in these two places we saw that one of them changed and changed the other one also. Here only one of them changed, again here only one of them changes, not both QA and QB. Finally, so now let us move to step T7. So at T7 R is pulled down to 0, so both R and S are 0. So from T7 to T8 you will see that QA and QB will keep their old values, QA at 0 and QB at 1. Let us now assume that at time t equal to 9, S became 1. If S comes on when R is 0, then QA will go on, right. So when S comes on, QB goes 0, because of which QA goes on, right. So this is the sequence, because of the green line going 1, the purple line will go to 0 and the red line will go to 1. So far everything is all right. Let us look at time step 9. So at time step 9, R also comes on, right. If R comes on, that will bring QA to 0. You can see that here, if R comes on, then QA should go to 0. So now this is a peculiar time step. What has happened now is R and S are both at 1 and QA and QB are both at 0. Okay. Now for some reason, let us assume that at T10 both R and S are pulled down to 0. So they both are changing from 1 1 to 0 0, right. So if R is changing from 1 to 0, S is changing from 1 to 0, and the other two inputs, the QA and QB are already at 0. Now let us see what is supposed to happen to QA first. So R is changing from 1 to 0 and QB was already at 0. So if you look at what will happen to QA, this is 0 and so this is changing from 1 to 0, QB is at 0, so QA will try to change to 1, right. Let us say at the same time I was evaluating S, right, before this QA changes to 1, let us assume that QA was already 0, right. So if it is at 0, let us now evaluate S. This was at 0 and S also went to 0, so 0 and 0, 0 or 0 gives 0 and the NOR will make it 1. So if both R and S simultaneously go to 0, QA and QB both will go simultaneously to 1, okay. So but that itself is not the problem. If both of them go simultaneously at 1, so let us say both these gates have the same amount of delay, that is the amount of time that a change in input takes to propagate to the output. let us say if both of them have the same amount of delay, then QA and QB both would have turned to 1 in this time point. If both of them turns to 1, now this is a 1 and S is 0, so QB will try to change to 0. Similarly, QB is a 1, R is 0, QA will try to change to 0. So QA and QB both will again try to go to 0. So both of them will try to go to 1 simultaneously, and then they both will try to go to 0 simultaneously, and then again it will go back to 1 and again go back to 0 and so on, and it is not going to remain stable at 0 or 1. So this is not the definition of a stable multivibrator, right. The outputs, both the outputs QA and QB will start oscillating indefinitely. So this happens at the peculiar time. So this is a very careful condition. So in English they call it the perfect storm, the correct set of conditions which results in something like this. The correct set of conditions is if both QA and QB are at 0 and R and S were at 1 and they both change to 0 simultaneously. If that happens, this is a perfect storm that makes the outputs toggle, and no matter what you do, the outputs are going to toggle continuously. This is not a stable system. So if the inputs stabilize down, at some point the outputs should stabilize. That is the nature of circuits. So if the inputs are not changing, if R and S come to a stable state, let us say both R and S remain indefinitely at 0, the outputs will still keep toggling from 0 to 1 to 1 to 0 and so on. This is an undesirable condition. So even though the circuit's implementation is when both are 0, the previous values are retained. If R is 1, you can see that QA goes to 0 and QB goes to 1. If S is 1, QA goes to 1 and QB goes to 0, and if both are 1, they both go to 0. So this is what the circuit does, but this is actually causing something undesirable, because if both R and S went from 1 1 to 0 0 at the same time, then the outputs being 0 0 will both try to switch to 1 1, and then they will again switch back to 0 0 and then so on indefinitely. So this is a bad thing. So what we are going to do is we are going to characterize our SR latch. So we have what is called a SR latch here. The name is there because of two signals S and R. So we have two signals S and R, and we are going to define this in a characteristic table. So characteristic table is actually simple. It has the two inputs S and R, and we capture only the one of the outputs. So the state of a latch is usually just 1. So the other one is just a complement. Let us not worry about the other one right away. So what we are going to use is we are going to state that the current time point, this is the value, and if the inputs change, what will be the next value. Remember, the next value should depend on the current value as well as the inputs that have come in. So we will use the symbol q, qn minus 1 or q of t to denote what is the value at the current time point, and we will use q star qn or qt plus 1 for what is supposed to be at the future. So it's from time t to t plus 1 is going from current to the future, and then t plus 1 to t plus 2 is again from that current to its future and so on. We will use these notations, either we will use q and q star, qn minus 1 and qn, or qt and qt plus 1. So we will use them as much as possible. I will try and use qt and qt plus 1 to represent this. So let us see what a characteristic table is. If both are 0, then q star or q in the future is the same as q in the current value. So if current value is q, it could be 0 or 1, q star will go to 0 or 1 depending on q. Now if R is 1 and if S is 0, q star or the next value will always be 0 no matter what the current value of q is. Similarly, if S is 1 and R is 0, the output q will always be 1 no matter what previous value is. So if the current value is 0, it will still go to 1. If the current value is 1, it will remain at 1. So that is the meaning of SR being 1 and 0. And finally, if both S and R are 1, this is undesirable. We do not want 1 1, because this 1 1, S and R being 1 1, and if for whatever reason we saw that QA and QB are both 0, there is a problem. right. So, we do not want that condition. So, we will say that that condition is undesirable or it is undefined, right. We will use this undesirable or undefined. So, the key thing is, if you notice in the previous case, right, if QA is 0, QB is 1, and if QB is 1, QA is 0. So, in fact, instead of calling them QA and QB, we could call them Q and Q complement, which is what I did in the previous slide actually. So, instead of calling them QA, QB, assuming that these are two different things, if we did not have this condition 1, 1 leading to a 0, 0, let us say 1, 1 never happened, you can never give 1, 1 as an input to the circuit. Let us say somehow you guarantee that S and R can never become 1 at the same time, then the output QA and QB will be complement of each other. So, it is okay to give only one of them and not specify the other one. We assume that in all these cases we are talking about QA of t and QA of t plus 1 versus QA of t, we will just call that Q from now on. You can also design the same thing using a NAND based circuit. So, we have done the same thing as before, except that, so this is also like two NAND gates which are coupled to each other, right. So, this kind of alignment is called a cross coupled alignment. So, we have two gates which are feeding which are being fed by R and S, and there is some cross coupling between the outputs. So, this circuit is called a cross coupled NAND circuit. The previous one we saw was a cross coupled NOR circuit. So, in a cross coupled NAND circuit, the behavior is as it was before. If S is 1 and if R is 0, the output Q of t plus 1 will be a 1. If S is 0 and R is 1, output Q of t plus 1 will be a 0. If both are 1, you will get Q of t. If both are 0, it is undesirable. So, this is the difference between a SR latch based on NAND versus an SR latch based on NAND. So, 0, 0 is undesirable for a NAND based latch, however 1, 1 is undesirable for a NOR based latch, and in a NAND based latch 1, 1 will keep the previous value, it will retain the previous value of Q and Q bar, whereas 0, 0 will retain the previous value in the NOR based SR latch. So, these are the four, so these are basic conditions. SR latch could be either NOR based or NAND based. In a NOR based latch 1, 1 is undesirable, and in a NAND based latch 0, 0 condition is undesirable. So, we will see why this is called a latch and all this undesirability and other things, how to get rid of it and so on from the next module onwards. So, as of now, just realize that SR latch and SR latch based on NAND or NOR have some condition which is undesirable, somehow you should make that condition go away. So, what we will do in the next module is we will see how to make that condition go away. So, this brings me to the end of module 18, and I will see you in the next module where we will talk about how to get rid of the condition where S and R are taking the same value, right. We will see that in the next module. Thank you and see you soon.